Hey everyone, and welcome to the explainer for optimization and error handling with data-types-solidity. I'm super excited to be your host today on behalf of Forge College. So we're making our way through the Solidity from Zero course, and we are building right up to our capstone project, Comprehensive Smart Contract Development. Now in our previous lesson, Testing and Validation for Solidity Integration, we laid down this fantastic, rock-solid baseline, right? The code works, the tests pass, and the logic is totally sound. But let's be totally honest with ourselves here. It's a bit heavy. It's kind of like having a sports car that runs perfectly, but for some reason you're driving around with a trunk completely full of bricks. So today, we are taking that baseline code and giving it a much-needed, highly efficient smart contract makeover. We're going to dive deep into optimization and bulletproof error handling. Let's get started.
Okay, let's quickly run through our agenda. First up, shrinking the storage footprint. Second, bulletproof error handling. Third, the refactoring process. And fourth, proving your gas savings.
All right, Section 1, shrinking the storage footprint, decluttering your structs. Let's jump in.
To put all this into perspective, using an oversized data type like a UN256 for a tiny little number is exactly like renting a massive, industrial-sized warehouse just to store a single pair of socks. I mean, it's a completely comical waste of space, right? But more importantly, in Web 3, it's a huge waste of gas. We've got to start finding appropriately sized containers for our data.
So to clean up this giant warehouse of ours, we're going to use our three main cleaning supplies. I actually like to call these the big three optimizations. We've got integer narrowing, boolean packing, and converting short text to fixed length bytes. Seriously, mastering just these three techniques alone will instantly level up your Solidity code from amateur to professional.
Let's start with the first one on that list, integer narrowing. This simply means finding variables, things like small counters, simple IDs, or maybe timestamps, and shrinking them down to the narrowest type that's safely possible based on your domain constraints. You definitely don't need a 256-bit integer to count up to 10.
This comparison brilliantly illustrates our first makeover. Over on the left, we've got our bloated baseline code, massive UN256 fields for an ID and a timestamp. On the right, look at that! We've converted them into a snug UN32 for our ID. And by the way, that can still count up to over 4 billion, so we're safe there. Plus a uint48 for our timestamp, which totally covers realistic date ranges way into the future. They easily fit the ranges we need while saving absolutely precious space in our storage slots.
Next up in our toolkit is Boolean packing. Now what's really fascinating here is understanding how the Ethereum virtual machine actually works under the hood. The EVM processes data in 32-byte chunks. Actually, let me clarify that. If you declare a simple true or false Boolean, it might just hog that entire 32-byte slot all to itself if you aren't super careful with your ordering. So instead of letting every single flag act so selfishly, we can pack them tightly together.
Just look at this before and after. On the left, two separate, sprawling Booleans just eating up unnecessary space. On the right, we've neatly folded them into a single uint8 variable that we just named flags. By using simple bitwise operations, we can literally store up to 8 different true-false values inside just this one tiny 8-bit gear. It is incredibly efficient.
Moving right along, our third storage optimization tool is transitioning from dynamic strings to fixed-length bytes. See, whenever you use a standard string in Solidity, the EVM has to dynamically allocate memory and figure out its exact size on the fly. That calculation, plus the storage overhead, it's a massive gas guzzler.
By simply swapping a dynamic string for a bounded bytes 32 type, we do force a hard limit of 32 characters, sure. But we make frequent operations for things like short notes, maybe token symbols, or quick tags significantly cheaper. Rule of thumb, if you know for sure your text is going to be short, never use a dynamic string.
Okay, Section 2, bulletproof error handling, explicit machine-readable reverts. Let's check it out.
I absolutely love this analogy. Explicit error handling is exactly like having a really strict but super professional bouncer at a club. If you do something wrong, they don't just toss you out onto the pavement in total silence, right? They tell you exactly which rule you broke so you can go fix it. Vague errors are completely useless to integration partners who are out there trying to interface with your smart contracts.
So the crucial takeaway here is we need to move away from these long conversational sentences. Look at the left side. That long string literally costs you gas just to store it in the contract code. That's wild. Instead, look at the right. We shift to sharp, explicit, machine parsable revert tokens, like creator 0 or note too long. Not only is it cheaper to deploy, but it allows another computer program to easily read and react to the exact error that just happened.
All right, Section 3, the refactoring process. Welcome to the Smart Contract Lab.
This isn't just about randomly hacking away your code. It's a precise scientific method. You want to follow these steps religiously. First, branch off and create a safety checkpoint in Git. Always have a backup. Second, run your baseline test from Lesson 3 so you have a solid record of success. Third, apply your struct compressions and error refactors. And finally, Step 4, rerun your tests to ensure behavioral parity.
Now, what happens if you hit Step 4 and suddenly a test fails? Don't panic. It usually just means you intentionally changed an API type. For example, if your old test is passing a string to a function, but you just beautifully optimize that function to accept a bytes 32, well, the test absolutely should fail. Just update the test to match your new optimized reality. Or just add a quick compatibility wrapper. Easy fix.
And finally, Section 4, proving your gas savings, the debug report.
So, your final deliverable for this module is the debug report. This is your verifiable artifact that essentially proves you did the work. It absolutely must include your exact code diffs, proof of at least 3 specific optimizations we talked about, validation that your tests are still passing, and of course, the actual before and after gas metrics that prove you saved real money.
Before we wrap up today, let's do a really quick recap. If you remember nothing else from this explainer, please etch these 3 core principles into your brain. Keep your data types as narrow as safely possible, pack your variables tightly to minimize those 32-byte slots, and keep your revert tokens sharp and explicit. This right here, this is the foundation of professional smart contract development.
So as you prepare for the final capstone assembly lesson, I want you to take a hard look at your code base and ask yourself, what other hidden gas guzzlers are still lurking in your baseline code, just waiting to be optimized? Get in there and start cleaning up that warehouse. Thank you so much for joining me for this explainer on behalf of Forge College. Be sure to visit forge.college to learn more about this subject, dive into more advanced Web3 topics, and continue your journey to becoming a top-tier developer. See you next time.